Hello viewers, in today's session we are going to discuss one important definite integral, right? So here in this class we are going to evaluate the value of this definite integral in which we are going to use some important properties of definite integrals and some standard result from indefinite integrals, right? So here we have to evaluate this integral from 0 to pi, and the integrand is x divided by 1 plus cosine square x. So let us take this integral as I, right? So we know that an important property of definite integral which says that if we have an integral from 0 to a f of x dx, then this integral is equivalent to 0 to a f a minus x dx, right? So what we do in this integral, we replace this x by a minus x, right? So here we have 0 to pi, so the value of a is pi, and the function f of x is given by x over 1 plus cos square x. So let us apply this property to this integral, and let us call this integral as integral number 1. And applying this property, we can now write 0 to pi, and here we replace x by a minus x. So it means we have to replace x by pi minus x in the second step. So we have pi minus x, and here we have 1 plus cos square pi minus x, and this is dx. And now using some trigonometry, we know that cos of pi minus theta is given by minus cosine theta. So this is a standard result from trigonometry. So here we have 0 to pi, pi minus x, and here we have 1 plus cos pi minus x is minus cos x, and which is minus cos x square, right? So now we can write this integral as 0 to pi, pi minus x, and here we have 1 plus minus 1 square is positive, so we have simply cos square x, and here we have dx, right? So let us split this integral at this point, that is the negative sign pi minus x. So let us write it as 0 to pi. The first integral is pi dx over 1 plus cos square x. The second integral is negative. Here we have the negative sign, so this is 0 to pi. Here we have x dx over 1 plus cos square x, right? And now if we closely look at this integral, this is our original integral I, right? So now we can write it as 0 to pi. Here we have this integral. Let us take pi outside the integral because pi is a constant. So we have pi dx. Here we have 1 plus cos square x, and this integral may be replaced by I, right? And now taking this I to this side, we have I plus I, and this is pi 0 to pi and dx over 1 plus cos square x. I plus I is now equal to 2i, and taking this 2 to the denominator of pi, we now have I is equal to pi over 2 and 0 to pi, and here we have dx over 1 plus cos square x. So let us call this integral as integral number 2. So now let us convert this cos square x into secant square x. So we know that secant x is equal to 1 over cos x. It means cos x is equal to 1 over secant x, right? So I can be written as pi over 2. Here we have 0 to pi, and we can now write dx over 1 plus 1 over secant square x. For cos x we can write 1 over secant x, and simplifying this term we have pi by 2, this is 0 to pi, and here we have secant square x times 1 is secant square x. Here we have 1, and taking secant square x to the numerator, we have here secant square x, and here we have dx, right? Now here we can apply one important trigonometric identity, that is 1 plus tan square x is equal to secant square x, right? So let us write this secant square x as 1 plus tan square x, right? So we'll replace only this secant square x by 1 plus tan square x, and the secant square x in the numerator, it remains as such. So we have I, this is pi by 2, 0 to pi, we have secant square x dx, and here we have 1 plus tan square x plus 1, and here we have dx. So this is pi by 2, 0 to pi, this is secant square x dx, and here we have 1 plus 1 is 2, so we have tan square x plus 2, right? Now we'll solve this integral by making use of the concept of substitution method. So now before applying the substitution method to this integral, we'll make use of another important property of definite integral, which says that if we have the integral from 0 to 2a f of x dx, then this integral is given by 2 times 0 to a f of x dx, right? Provided f of 2a minus x should be equal to f of x. So this property is also an important property of definite integrals, which says that if we have 0 to 2a, so the upper limit is 2 times a, and here we have the function f of x, then this integral is equal to 2 times the integral from 0 to a, right? So now the upper limit becomes only a, that is half of 2a, and we have f of x dx. So this expression is valid only when this condition prevails, right? That is f of 2a minus x should be equal to f of x. So let us apply this property to this integral. Now see, here we have pi, right? So we can now write this integral as pi by 2, and we can write 0 to 2 times pi by 2, because there is no harm in writing pi as 2 times pi by 2, because 2 and 2 are going to be cancelled, right? So we can write pi as 2 pi over 2. So now our a, this a is equal to pi by 2, and here we have 2, and f of x is secant square x over tan square x plus 2, and here we have dx, right? So now we have to see whether this condition is applied or it is valid for this function. So here f of x is secant square x over tan square x plus 2. So f of 2a minus x, so 2a, a is pi by 2, so we have f 2 times pi by 2 minus x, which is again f of pi minus x, right? So f of pi minus x is given by secant square. Here we have, for x we can write pi minus x, then we have here tan square pi minus x plus 2, right? So now we know that secant pi minus x is given by negative of secant x, and similarly tan of pi minus x is given by negative of tan x. So secant square pi minus x is square of this term, that is negative secant x squares, and it becomes a positive, so we have simply secant square x. And similarly tan pi minus x is negative tan x, and when we make the square, then this negative sign becomes positive, so we are left with tan square x, and here we have 2. So this function is again equal to this one, which is our original function f of x, right? So we can see that this condition holds for this function, that is secant square x over tan square x plus 2, right? So now we have pi by 2, 0 to 2 times pi by 2 secant square x over tan square x plus 2 dx. So now we can write this integral as here we have pi by 2. So now we have 2 times, because here we have 2 times 0 to a. So we have 0 to a, which is pi by 2. So we have here secant square x over tan square x plus 2, and here we have dx. So now this is our integral I. Here 2 and 2 get cancelled, so we have I is equal to pi times 0 to pi by 2. Here we have secant square x over tan square x plus 2 dx. Now let us make the substitution here, and we can take u is equal to tan x, right? So we can differentiate u with respect to x, so du over dx is secant square x. So we have du is equal to secant square x dx, right? So here we have secant square x dx, and let us change the limits accordingly. So here x varies from 0 to pi by 2. So when x is 0, then u is tan 0. Tan 0 is 0. And when x is pi by 2, we have u is equal to tan pi by 2. And this is not defined, so we can write it as infinity, right? So now we have I is equal to pi, and we have 0 to infinity. Here secant square x tan x can be written as that is du, and in the denominator we have u square plus 2, right? So this is pi, here we have 0 to infinity du, and this is u square plus 2 can be written as the square of square root of 2, right? Okay, so now we have a very standard integral, and we know from indefinite integrals, that is dx over x square plus a square is given by 1 over a and tan inverse x over a, right? So we are going to use this result to this integral. So we have pi, here we have the variable u, here we have x, and this is a square. A square is our square of root 2. So a is square root of 2. So we have 1 over a, 1 over square root of 2. Then we have tan inverse x over, that is u over square root of 2. And we have the limits from 0 to infinity. So now let us substitute the limits, and we'll take the difference. So we have I, and we can take square root of 2 outside. Here we have pi over root 2, and we have simply tan inverse u over square root of 2, 0 to infinity, right? So we have pi over square root of 2, and when we take u is equal to infinity, we have simply here tan inverse of infinity and then minus tan inverse of 0 over square root of 2, which is simply 0, right? So first we take u is equal to infinity, then u is equal to 0. So we have tan inverse infinity minus tan inverse 0. So here we have now pi over square root of 2. Tan inverse infinity is pi over 2 and tan inverse 0 is 0, right? Because we know that tan pi by 2 is infinity and we have pi by 2 is equal to tan inverse infinity, right? And similar is the case with tan inverse 0. So now we have pi over square root of 2 times pi over 2. So we have pi square over 2 times square root of 2, right? So whereas the value of this integral is equal to pi square over 2 times square root of 2. So this is how by making use of the concept of the properties of definite integrals and other results from trigonometric functions, we can evaluate this integral. So the value of this integral is given by pi square over 2 times square root of 2. So 2 times square root of 2 is 2 root 2.